We're ready now to get started on chapter 21. That's about electric charge and electric field. This is a really important topic to study, and one of the reasons we study it is just because of water. Of course, we couldn't live without water, and water is so important because the cells in your body function by dissolving essential biological molecules, and that only happens because water has electrical properties. So we're going to look at the properties of electric charge, forces, and fields. Let's start this section with an experiment. If you have another human being in your house, a couple of balloons and some string, each of you blow up a balloon too close to the same size and tie it onto a string. Rub the balloons really hard against your head or a wool sweater. Hold up the balloon by a string and try and bring it close to your friend's balloon and see what happens. If you don't have the means to do this at home, here's one that I did at home.
Okay.
All right, so what we see happened in our experiment is that after rubbing the balloons on our heads and trying to bring them together, they wouldn't come together and they were actually being pushed apart. So some conclusions we can draw from this is that when we rub the balloons on our head, they each acquire charge. Must be the same kind of charge because our heads are fundamentally the same and our balloons are the same. And that the balloons won't come together tells us that there must be a repulsive force between those two charged objects. These are the things we're going to be looking at in this chapter. First, we'll just get a tiny little bit of nomenclature down. The first is that the symbol for charge is Q. I would say mostly we use a lowercase q, but sometimes it's going to be uppercase. And the units for charge are coulombs. That's an uppercase C. That's after Charles Coulomb. He was a French engineer and physicist in the 1700s. He studied charge a great deal, and we'll learn more about Coulomb's law. Of course, he's not the only scientist who studied charge. Pretty much all the people on the globe studied charge and learned much about it. We know going back in ancient history that Greeks discovered around 600 BC that amber rubbed with wool would attract things. We know now that that amber collected an electric charge. And in fact, the word electric comes from the ancient Greek word electron, meaning amber. We know that atoms make up everything, and electrons, protons, and neutrons make up atoms. Electrons and protons both have electric charge, and neutrons do not have electric charge. Um, Electrons and protons are oppositely charged, so we say that protons have a positive charge and electrons have a negative charge. That turn of phrase was coined by Ben Franklin. It's not inherently meaningful, the words positive and negative. It just means they're opposite. And neutrons have no charge at all. Atoms are held together by the attractive electric force between the positive nucleus, where the protons and neutrons are, and the negative electrons, which are orbiting outside. Why the nucleus doesn't blow apart is also very interesting. That's because of the strong nuclear force. Okay, what we know about the charges of our protons and neutrons is that they're equal and opposite, and they both have the same size. And the size of that charge is called the fundamental unit of charge, and that has a symbol of E. Its value is 1.6 times 10 to the minus 19 coulombs. So the charge on a proton is plus E, and the charge on an electron is minus E, and the charge on a neutron is 0. Something super interesting about charge is that charge is what we call quantized. What that means is that every charge in the universe, I guess that we know of so far, is an integer multiple of that fundamental unit of charge E. Except for quarks. Quarks are weird. Quarks can have like a third or two-thirds of a charge. So except for quarks, every single charge in the universe is a multiple of that charge E. Could be a positive or negative, but still is a multiple. If you think about that, it means that the total charge on on any object would be however many protons it has times the fundamental charge plus however many electrons it has times the negative fundamental charge. So that equals the total charge Q on any object. The last thing that we'll say about charge is that charge is conserved. That's also pretty interesting. You can move charge around, but you can't change it. You can't make it up and you can't destroy it. So the total amount of charge in the universe is always the same. Okay, let's just do one quickie example now. How many electrons would it take to make up -1 microcoulombs of charge? Well, we know the total amount of charge would be the number of protons times E, no protons at all, plus the number of electrons times the fundamental unit of charge E, but it's negative because it's a proton. So the number of electrons would be the total charge divided by minus E, so -1. Note about prefixes here, this symbol mu, mu, that means 10 to the -6. So that's 10 to the -6 coulombs. That's divided by -1.60 times 10 to the -19 coulombs. Just grab my calculator and do that division. And what we get is 6.25 times 10 to the 12. That is a lot of electrons. The motion of charges is going to be important. What we know about the motion of charges is that protons do not move. Those are stuck inside the atoms, and electrons are free to move around. We know that charge will move easily through a conductor, and charge will not move easily through an insulator. Semiconductors are special. Sometimes charge moves and sometimes it doesn't. So if we want to look at an example, let's say we had a plastic rod and we charged it up full of negative charges. If we touch that rod to a metal sphere, some of the charges will come off and they'll come onto the metal sphere. If that metal sphere touches another plastic rod, none of the charges will come down this rod onto the next metal sphere. So that's what happens when our conductor hits the insulator. The charges won't travel. If we had instead our charged plastic rod touching the metal rod, some of the charges will come off. Of course, what we learned with our balloon experiment is that like charges repel, so they're going to try and get away from each other. To do that, some of those will move into the metal rod. Once they get to the next metal sphere, they'll go onto that metal sphere as well. So this is just an illustration about how charge will move through a conductor, but it will not move through an insulator. Here are some general conclusions about charge. Neutral objects will not attract each other. A charged object will attract a neutral object. If you want to try that out, and if you still have that balloon hanging around, you can try and see if it'll stick to your wall. Rub it really hard on your head and see if it'll stick to the wall. That's a case of a charged object attracting with a neutral object, and we're going to talk about that. If two objects have the same kind of charge, either both positive or both negative, they're going to repel. And if objects have different charge, they're going to attract. So if one is positive and one is negative. The size of that force between any two objects, it depends on two things: how much charge there is and how far apart they are. If they're close or if they have big charge, we get a big force. If they're far apart or if they have small charge, we have a small force. For a quick look on how charging and discharging happens, if we have a charged plastic rod, so imagine someone has rubbed that on their head, it's full of electrons, so it has lots of negative charge, and we bring it close to a metal surface. So that's your first step, is you just bring it in close. Then what happens, as soon as it touches, those charges start to transfer. So touch, transfer. This is a pretty fast process. So the charges come off that rod and they go onto the metal sphere. Now we know that these guys repel, so they're going to spread out. And this process happens very fast. So they're all spread out here. Once they're all spread out, they stay still, and we say that this new metal object now is in electrostatic equilibrium. Electrostatic equilibrium because all of the electric charge is still and it's not moving, still with no acceleration. That's a term that we're going to come back to a few times in the course, electrostatic equilibrium. Okay, discharging happens in a similar way. Let's say we have a metal object that has very few electrons on it. So it's lost a bunch of electrons. That means overall it has a positive charge. And let's say you come up to it and you put your hand on this metal object. If you're trying to think about a case where this might happen, sometimes on a summer day you touch your car and you get a shock, or in your home you might touch a metal doorknob and get a shock. This is that sort of a thing. So what happens is that you're full of charge, you're going to touch it, probably feel a shock, and that shock is a transfer of charge. Electrons leave you and they go on to the object. So you're standing there, you have a bunch of protons and electrons all throughout your body. The electrons go into the metal object, and more or less one electron goes close to every proton and it ends up neutral. But the electrons have left you and you end up positive. Okay, so that's how discharging would work.